If the entire solar system, from the Sun out to Neptune, measured merely 0.4 millimeters, smaller than a single grain of sand, the center of the Milky Way would be 11 kilometers away. The entire galaxy would span 42 kilometers in width, and within the very heart of it, the supermassive black hole Sagittarius A would be just 2 micrometers big, smaller than a simple cell. The thing governing 200 billion stars would be invisible to your eyes. Scale is not just about size, it is actually about comprehension. When we shrink down the universe, we discover that what is truly small is our own intuition, and that is why we keep measuring. If the universe seems bigger to you now than you have already started to see. Welcome to the SunkenVale channel. The Milky Way does not represent a poetic abstraction, but a physical structure defined by strict geometric parameters. It concerns a stellar system classified as a barred spiral, presenting an approximate diameter of 100,000 light-years. To comprehend this scale through a comparative model, consider that if our galaxy were reduced to the size of a grain of sand with 1 millimeter in diameter, the observable universe would have the extension of a sphere of 930 meters. However, the internal proportion is even more extreme. The thickness of the galactic disk is merely 1,000 light-years, which establishes a ratio of 100 to 1. This morphology equates to the proportion of a vinyl record or a standard sheet of paper, where the width dominates almost the totality of the mass viewed in profile. At which coordinate of this planet are you right now? Before we advance to the astrophysical data that can redefine your perception of the universe, mark your presence, subscribe. Without this signal, you might miss the next blocks of information, and what comes next changes everything. The distribution of mass inside this disk is not uniform. The existence of 100 to 400 billion stars is estimated. The solar system sits in the Orion Arm, a substructure located about 27,000 light-years from the geometric center. This peripheral position is fundamental for biological stability, avoiding the radioactive density of the central regions. The stellar density in the core is of such an order that if we were situated there, the night sky would contain stars with brightness equivalent to the full moon, separated by minimal distances of just a few light weeks instead of light years. At the absolute epicenter of this structure resides Sagittarius A, a supermassive black hole. The orbital data of nearby stars like S2 confirm that this object possesses a mass of 4.1 million solar masses. All this density is compressed into a Schwarzschild radius of approximately 12 million kilometers. For scale purposes, if the Sun were a human cell, Sagittarius A would be the size of a blue whale, exerting a gravitational influence that governs the motion vector of billions of objects in its surroundings. The galactic disk divides itself into two main components, the thin disk and the thick disk. The thin disk contains younger stars like the Sun and most of the interstellar gas necessary for the formation of new celestial bodies. Yet the thick disk extends above and below the plane, harboring older stars with low metallicity. This separation indicates distinct episodes of matter accretion throughout 13.5 billion years. The rotation of this system is differential, The stars close to the center complete an orbit more rapidly than those at the edges, which theoretically would cause excessive winding of the spiral arms, the so-called winding dilemma. This phenomenon is resolved by the density wave theory, which proposes that spiral arms are not fixed structures, but zones of higher stellar traffic density, where gas is compressed to generate new stars. The population sampling of the Milky Way reveals that the Sun is a statistical exception. About 75% of galactic stars are red dwarfs, spectral type M, stars of low mass, reduced temperature, and longevity that can surpass trillions of years. In comparison, the Sun is a yellow dwarf, type G, belonging to a minority of 7%. If every star in the galaxy were a grain of rice, we would have enough volume to fill an Olympic stadium, but only a small fraction of those grains would be visible to the naked eye from the terrestrial surface. The majority of stellar mass remains hidden by interstellar extinction, the blocking of radiation by clouds of dust and gas that permeate the galactic plane. The orbital dynamics of the solar system around the galactic center occurs at a velocity of 220 kilometers per second, or 800,000 kilometers per hour. Despite this massive vector velocity, the orbital period, known as the galactic year, is approximately 230 million years. The last time Earth occupied the current position in galactic space, the first dinosaurs were beginning to emerge in the Triassic period. The total displacement of Earth since its formation equates to only 20 complete laps around the core. This constant orbital movement leads us to consider what exists beyond the visible frontiers of the disk, where luminous matter loses its dominance to invisible forces. The transition from the disk to the galactic periphery reveals an even more ancient and mysterious.
The structure of the Milky Way extends itself far beyond the visible limits of the disk of 100,000 light-years discussed previously. Enveloping the entire stellar mass and the gas, there exists the galactic halo, a spherical component of low density but of critical kinematic importance. If the galactic disk were compared to a 1 real coin, the halo would be an invisible sphere that would envelop the entire room where that coin is deposited. This region harbors the oldest citizens of the system, the globular clusters. The globular clusters are dense spheres that contain between 100,000 and 1 million stars, all gravitationally bound in a volume of merely a few tens of light-years in diameter. There exist about 150 of these objects orbiting the galactic center on highly elliptical trajectories. The density at the center of a cluster like Omega Centauri is such that the average distance between stars is only 0.1 light-years. In terms of scale, if the distance between the Sun and the nearest star, Proxima Centauri, were 1 kilometer, inside a globular cluster, that distance would be reduced to less than 20 meters. These stars possess ages that date back to 13,000 million years, formed in an epoch when the universe was composed almost entirely of hydrogen and helium, with a scarcity of heavy elements. However, the halo reveals a mathematical anomaly that defies baryonic physics. Upon measuring the rotation velocities of the stars at the outer edges of the galaxy, astronomers observed that they move as fast as the stars closest to the center. According to Kepler's laws, the velocity should decrease with distance, in the same way that the outer planets of the solar system orbit more slowly than the inner ones. This phenomenon, known as the galactic rotation curve problem, implies the existence of an invisible mass that provides additional gravity: dark matter. Dark matter does not interact with electromagnetic radiation. It does not emit, reflect, or absorb photons. It constitutes approximately 85% of the total mass of the Milky Way. Without this component, the centrifugal force of the orbiting stars would surpass the gravitational attraction of visible matter, and the galaxy would fragment itself, dispersing its components through the vacuum. Imagine a carousel spinning at a speed 1,000 times superior to its structural capacity, but kept cohesive by invisible steel cables. Dark matter is those cables. The Milky Way is inserted into a dark matter halo that extends for over 1 million light-years, a scale that makes the stellar disk seem like a microscopic detail in the center of a colossal infrastructure. Departing from the individual domain of our galaxy, we enter the local group. This is a set of more than 50 galaxies bound by gravity. The local group covers an extension of 10 million light-years. If the Milky Way were a hydrogen atom, the local group would be the size of a human cell. The three main members are the Milky Way, the Andromeda Galaxy, M31, and the Triangulum Galaxy, M33. The remainder of the population is composed of dwarf galaxies, such as the Magellanic Clouds, which function as satellites orbiting the main mass. The Andromeda Galaxy is the most massive object of the group, possessing about 1 trillion stars, double that of the Milky Way. Currently, Andromeda and the Milky Way approach each other at a speed of 110 kilometers per second. This motion vector will result in a head-on collision in approximately 4,000 to 4,500 million years. Despite the term collision, the probabilities of a direct crash between two individual stars are virtually null due to the vastness of empty space between them. If two stars were ping-pong balls, the average distance between them would be 3,000 kilometers. In the event of the merger, the two spirals will be dismantled by gravitational tidal forces, resulting in a single and gigantic elliptical galaxy, temporarily named Lactomeda. The vacuum between the galaxies of the local group is not an absolute nothing, but a diluted intergalactic medium. The average density is less than 1 atom per cubic meter. For comparison, the most perfect vacuum created in terrestrial laboratories still contains billions of atoms in the same volume. This spatial desert is so vast that the light of Andromeda takes 2.5 million years to reach us. This means that when observing Andromeda today, the captured data referred to the period when Homo habilis was beginning to utilize the first stone tools on Earth. The space between the galaxies is the largest cemetery of photons in the universe, where radiation travels for eras without encountering any material obstacle. The maintenance of the stability of the local group is a precarious balance between the expansion of the universe and gravitational attraction. While the fabric of space expands on cosmological scales, local gravity is strong enough to keep these galaxies united. However, this archipelago of light is merely a small cell in a much larger organism. The local group is not static, it is pulled by large-scale gravitational currents that take it towards even denser mass concentrations. The technical analysis of this chapter demonstrates that the Milky Way is not an isolated island, but a component of a binary system on a collision course immersed in an ocean of invisible matter. The scale of the local group is the first step for the comprehension of the macrostructures that define the architecture of the cosmos. The transition to the next level of magnitude reveals that even galaxy clusters are merely filaments in a network that spans the entire observable volume.
The comprehension of the terrestrial position in the cosmos demands a radical shift of scale. Upon leaving the limits of the local group, we enter the domain of the Virgo supercluster. This structure is not a solid object, but a cluster of approximately 100 groups and clusters of galaxies situated within a diameter of 110 million light-years. The gravitational center of this system is the Virgo cluster, a dense galactic metropolis that shelters between 1,300 and 2,000 galaxies. To visualize the scale, if the local group were a single-family residence, the Virgo supercluster would be equivalent to a medium-sized city. However, in 2014, the definition of this city was reclassified. The kinematic data of thousands of galaxies revealed that Virgo is merely an appendage of a structure much more vast, Laniakea. Laniakea, a term that in Hawaiian means immeasurable heaven, is a supercluster that spans 500 million light-years in diameter and contains a mass equivalent to 100 quadrillion suns, or 10 to the 17 solar masses. The characteristic that defines Laniakea is not its visual appearance, but its gravitational flow. Imagine a map of watershed basins where each drop of water flows toward a central valley. In Laniakea, the galaxies are the drops of water and the flows are dictated by gravity. The solar system is located on the extreme periphery of this structure. If Laniakea were the continent of South America, the Milky Way would be situated in a small coastal village in the extreme south. This megastructure contains 100,000 massive galaxies, all moving along invisible streamlines. The velocity of this displacement is dictated by the imbalance of mass in the fabric of space-time. The destiny of all galaxies inside Laniakea, including ours, is a point of convergence known as the Great Attractor. Located about 250 million light-years away, in the direction of the constellations of Centaurus and Norma, this point exerts a force of attraction equivalent to tens of thousands of galaxies. Flow velocity. The Milky Way moves toward the Great Attractor at approximately 600 kilometers per second. Zone of avoidance. The direct study of this phenomenon is hampered by the zone of avoidance, a region of the sky obscured by the gas and dust of our own galactic disk. The existence of the Great Attractor reveals that the expansion of the universe is not uniform on local scales. While the space between the superclusters expands, the mass inside Laniakea struggles to collapse toward this center of gravity. It is a physical battle between dark energy, which pushes galaxies apart, and gravity, which attempts to reunite them. The architecture of the universe is defined more by what is missing than by what is present. Among the filaments of galaxies that compose Laniakea and other superclusters, there exist the cosmic voids. The most notable is the Boots void, a sphere of almost nothing with 330 million light-years in diameter. In a volume of space of this size, the standard theory would predict the existence of at least 10,000 galaxies. However, the Boots void contains fewer than 100. If the Milky Way were in the center of this void, terrestrial astronomers would not have discovered the existence of other galaxies until the decade of 1960, because the sky would be in absolute darkness in all directions except for the stars of our own neighborhood.
The human perception of the cosmos is limited not by technological capacity, but by the finite speed of information in a vacuum. The concept of the observable universe establishes a sphere centered on the observer, whose radius is determined by the distance that electromagnetic radiation has traveled since the start of thermal expansion, 13,800 million years ago. However, due to the metric expansion of space during the journey of these photons, that radius is not 13.8 billion light-years, but approximately 46.5 billion light-years. This results in a total diameter of 93 billion light-years. To establish a comparison of absolute scale, if the Milky Way, with its 100,000 light-years of extension, were reduced to a small human cell of 20 micrometers, the observable universe would be a sphere with 18.6 meters in diameter. If our galaxy were a 1-cent coin, the visible universe would have the dimension of a sphere with more than 17 kilometers in width. Outside this frontier, there exist galaxies and structures whose signals have not yet reached Earth, and, due to the acceleration of expansion, perhaps never will reach. The detection of the distance between remote galaxies relies on the phenomenon of the redshift or redshift. Different from the conventional Doppler effect, which involves the movement of an object through space, cosmological redshift is a consequence of the stretching of the fabric of space itself. While the photon travels, the space under it expands, stretching the wavelength of the radiation. The Hubble-Lemaitre law quantifies this process with precision. The Hubble constant, currently estimated at 70 kilometers per second per megaparsec, indicates that for every 3.26 million light-years of distance, galaxies move away from us 70 kilometers per second faster. This creates a critical frontier known as the Hubble sphere. Beyond this radius, the recession velocity of galaxies surpasses the speed of radiation in a vacuum. To measure these magnitudes, astronomers utilize standard candles. Cepheid variable stars allow measurements up to 100 million light-years. For cosmological scales, we recur to Type 1a supernovae. These explosions occur when a white dwarf reaches the Chandrasekhar limit, 1.4 solar masses, resulting in a detonation with constant intrinsic luminosity. Upon comparing the apparent brightness captured by our sensors with the known real brightness, we determine the distance with mathematical rigor. When observing greater distances, we are inevitably analyzing the past. The physical limit of our vision is not a wall of solid matter, but a wall of photons, the cosmic microwave background radiation, CMB. This radiation was emitted 380,000 years after the initial event. Before that period, the universe was a dense, hot, and opaque plasma composed of hydrogen nuclei, helium, and free electrons. In the year 380,000, the temperature of the cosmos fell to approximately 3,000 Kelvin. That reduction of energy allowed nuclei to capture electrons, forming the first neutral atoms, named recombination. With the removal of free electrons, space became transparent to radiation. Due to the expansion of the universe throughout billions of years, this radiation was stretched until becoming microwaves with a temperature of only 2.725 Kelvin. The CMB is the oldest image of the universe. The temperature fluctuations in it represent the primordial density seeds. Without these infinitesimal irregularities, gravity would not have anchoring points to form galaxies. One of the most striking facts of modern physics is that the observable universe is in a process of informational isolation. The influence of dark energy, which comprises 68.3% of the total energy density of the universe, causes a constant acceleration in expansion. This implies that galaxies that are currently visible will end up crossing the cosmic event horizon. In a future calculated in hundreds of billions of years, all galaxies external to our local group will have disappeared beyond that horizon. The composition of the observable universe reveals a disproportion between the visible and the invisible. Dark energy, 68.3%, dark matter, 26.8%, and baryonic matter, 4.9%. This means that more than 95% of the content of the universe remains unknown. Measurements indicate that the geometry of the universe is flat with a precision of 0.4%.
The comprehension of the final fate of the universe demands the analysis of entropy, the physical measure of disorder that dictates the end of all useful processes. Currently, the cosmos traverses the stelliferous era, a period defined by the existence of active stars. This interval will end in approximately 100 trillion years. If the total duration of the universe were compressed into one terrestrial year, the entire era of stars would last only the first seconds of January 1st. The remainder of the year would be composed of an absolute and sterile darkness. The stars function as combustion engines that consume hydrogen. However, the reservoir of gas in galaxies is finite. When the stock of hydrogen gas is exhausted, stellar formation will cease definitively. The last survivors will be the red dwarfs, small stars that burn their fuel in an extremely slow manner. At the end of this term, the lights of all galaxies will go out,
leaving only cold stellar corpses in a vacuum in accelerated expansion. The transition to the degenerate era marks the end of matter as we know it. Physics predicts the decay of the proton, the fundamental component of the atomic nucleus. If the proton is unstable, all solid matter will disintegrate. This process would take a number of years, represented by the number 1, followed by 34 zeros. After the dissolution of baryonic matter, there will remain only the era of black holes. Through Hawking radiation, black holes lose mass slowly to the vacuum. The time necessary for a supermassive black hole to evaporate completely is a number followed by 100 zeros of years. The logical conclusion of this process is the heat death, or the dark era. The universe will reach the state of maximum entropy, where the temperature will be uniform and close to absolute zero. There will be no more stars, nor black holes, nor light. However, the physics of probabilities introduces a hypothesis about what exists beyond this finitude. If the universe is spatially infinite, the quantity of matter and energy must also be infinite. As there exists a limited number of ways to organize atoms in a certain volume of space, mathematics dictates that these configurations must repeat. In an infinite space, eventually one will find a region of space identical to ours. This implies the existence of exact copies of the Milky Way, of Earth, and of every historical event repeating infinitely through the vacuum. The complexity that we observe today is merely one of the infinite possible combinations of the cosmic code. The position of humanity in this chronology is that of an observer in a moment of maximum visibility. We live in a period where galaxies are still close enough to be studied, and stars still possess fuel. This window of clarity will last only a minimal fraction of the total history of reality. The acceleration of expansion is currently removing 20,000 stars per second from our horizon of visibility. The universe is not a static stage, but a dynamic system that walks toward total equilibrium. The existence of complex structures is a temporary byproduct of the flow of energy from the hot beginning to the cold end. Matter is the exception, the vacuum is the rule. Upon contemplating the thermal closing, the magnitude of the numbers presented serves to situate the biological experience in the structure of physics. The distance of 93 billion light-years of the observable universe and the time of 100 trillion years of the era of stars are parameters that define our bubble of existence. The analysis of this documentary closes here. The record of the data presented remains as evidence of the capacity of a planetary civilization to calculate its own position in the infrastructure of the infinite. The cosmos will continue its expansion, the stars will follow their fusion cycle, and entropy will advance according to fundamental laws. The knowledge of scale is the only tool that allows the observer to comprehend the vastness of the system in which they are inserted.